Hello, this is a supplementary lesson for physics covering section 18B in your textbooks, electrical charges. Just wanted to go over a couple of notes from some sections. So what we've had so far in electrical charges, I gave you that handout, that kind of simplified introduction to electricity. You've read section 18A in the textbook. This lesson is meant to touch on that a little, but more focus on this section 18B. That is your reading assignment today with some homeworks. And then also look forward to a lab, not next week, but actually starting Friday next week. And then going into a week from then. So 2 weeks from this week would be a lab. So real quick, so fundamentally there are two electric charges in the universe. They're designated as the positive and the negative charge. And we must remember, although they are inherent to matter itself, as I said in my first video, that at the elementary particle level, at electron level, at below the proton and electron level, the quarks, the elementary particles, the subatomic particles that make up protons and neutrons, they have a designated positive or negative charge, and so at that level, they truly do. There is a truly positive and a truly negative charge. Now, the interplay of the electrical charges and the forces between those elements, aren't as in big a play, because they are so close to each other inside the proton and inside the neutron that the strong nuclear force overrides. It rules the day inside the nucleus. Once we get outside the nucleus in that electron shell, then the electric charge, as far as a force, starts to take over in the atomic level. And in fact, it is that electric charge, and we said in that first video I gave you, it's a rather strong charge, or I should say a strong force in the universe. It ranks second, right below the strong nuclear force. So once we're in that electron shell area, the electric magnetic force rules the day at that point. And if the electron shell is rather large, a long distance from the nucleus, and there's lots of electrons, some of those electrons now in some materials can be loosely held. In other words, they can be free, they can be released if a force pulls on them strong enough from elsewhere to skip to another atom, to skip to another electron shell on another atom that has a large, maybe lots of electrons circling the nucleus. Now, practically speaking, when we're talking electricity, and especially in the realm of like household electricity, generating electricity at power plants, even in electrical circuits, it's this free flow of electrons that actually establishes what we call the charge. So practically speaking, in that sense, if an object, let me go off my notes here. So, as I said, protons and elementary particles that make those things, protons and neutrons, they are very fixed in the nucleus. The proton has a positive charge because it's made of 3 subatomic particles. 2 of them have a positive charge, 1 of them has a negative. When it balances out, it has a +1 positive charge. but it is firmly held inside the nucleus, the protons are. They are not, when we say a positive charge, we don't have protons, flowing all around the place, skipping from atom to atom. Remember, it's the combination of protons and neutrons in a nucleus that actually determines what element it is. So if we did have protons and neutrons skipping around and free flow just like we do with electrons, we would constantly have things changing what they are. They would be changing in from one element to the other as this happened, and we would have a wacky universe, okay? But those protons do not flow. It is the electrons that flow, and only in some materials. Remember, some materials hold those electrons tightly. They don't give them up, okay? Some of them hold them loosely, and they're like, okay, you can take off. And once one takes off, they can be like, I'll pull one in from over here, okay? And it happens all the time. Only in some materials, though, okay? And then it is this free flow of, electrons that we call electricity in a practical sense. So an overabundance of electrons on a particular material, we are saying then that is negatively charged, because we assign the proton the negative charge. So if it has an excess of, the proton is positive charge, the electron is negatively charged. If a material has an excess of electrons than it normally would in its proper configuration, where the atom has its correct number of protons and neutrons, and it balances out with the correct number of electrons. Okay, if we say that material has more electrons than that equilibrium state, we say it's negatively charged. Okay, and consequently, if a material is deficient in an electron or electrons, then we say it has a positive charge. Okay, it's not because that atom has acquired a positive proton, it's because there's a deficiency of electrons in one or more of the outer shells. Okay, so and by the way, the flow of electricity, what we consider current in our electrical systems, okay, it's that exchange of free electrons between materials, and again, it's between mainly certain materials. Not all materials like to do this, like to allow electrons to join their outer shells and release them to other ones. Not all materials do that, okay? But the ones that do, we call that electricity. We call that current. And what are the electrons trying to do? They're actually trying to establish equilibrium, electrical charge equilibrium between unequal areas of electrons. Okay, if there's an excess over here and a deficiency over here, and we connect a pathway between them, okay, it's the natural tendency for that to seek equilibrium. And that is what we take advantage of in our electrical systems. We take advantage of that. That is the tendency for charges. In your introductory chapter in that special reading we had on electricity in the textbook, and even in our lab, okay, they mentioned the law of charges. Now, that initial reading you had indicated 3 rules. The textbook indicated 2 rules, okay? They kind of combined what I have rule here 1 and 3. Okay, 1, I have like charges repel, okay? Opposite charges will attract each other. And then the 3rd rule, either charge will attract a neutral object. Okay, and the book combines that with the attraction up here for the opposite. But just remember, there's those 3 concepts. Okay, what if the 2 charges are the same? They're like charges. What if they're opposite charges? And what if there's a charge and a neutral object? Okay. Now, what makes an object neutral is that it's in electrical equilibrium. In other words, at the atomic level, and larger at the molecule level and that, there's an equal number of those elementary positive charges in the substance and the elementary negative charges, okay? And so really, even a proton we consider a neutron, which we consider a neutral part of the nucleus, is composed of charged elementary particles, okay? It consists of I believe, two positively charged particles and one negatively charged. It might be the reverse. I can't recall right now. But even the neutron itself, what makes it electrically neutral is the balance of those two. It comes out to a net zero charge, okay? But deep inside the neutron, there's charge involved there, okay? Remember, it's an inherent property of matter, of all matter, that it has electrical charge at the elementary level, okay? One of the concepts that you'll need to become familiar with in your textbook, the methods of charging to establish a charge on an object, okay? Your textbook goes through that. Friction, through contact, and then an important concept here that you need to really understand, especially to do well on your lab, is this concept of induction, okay? And induction is a redistribution of charges within an object when another charged object is brought in close proximity to it, okay? And the book describes it. The lab actually describes it real well. And so what's going on? Well, because matter is made of these charged particles at a small level, okay, and especially the electrons that are free to move, when we bring a charged object, okay, if this star over here down here is my object, I'm bringing a mass of negatively charged. If my hand here is the negatively charged object, it has an excess of electrons on it, and I'm going to bring it close to that positive charge, okay? It has a deficiency, okay? So what's happened is when I'm bringing that object close, it's actually repelling the electrons that are over here. There's still some electrons over there, but the ones that are over there are now going to the far side of that object because it is opposed, it is repelled by my electrons, my excess of electrons. And when it does that, it sends them to the far side. That leaves the side closest to my hand with a net positive charge, and they attract. Okay, and that's what causes the attraction. So in induction, what is it doing? Those movable particles, and what are the ones, practically speaking for us, they're the electrons. Okay, they redistribute themselves based on if a charged object comes by them, what do those electrons do? Do they want to back away, or do they want to get closer to that object? So get that concept of induction down. They mention in here on page 398 in your textbooks, so they have these methods for charging rods, and then they also have this electroscope, and that's actually the one we're going to be using in your lab. That we have that box-shaped electroscope in our lab equipment. Okay, so read over that section, and then in the text also read over the section about charging through induction, and that would be in that section 18b that you were to read today, and it's the one regarding the electroscopes. And of course their electroscopes here were the beaker shaped ones, and again we have the rectangular one in our lab equipment. Okay, the other concept to be familiar with in this chapter, we only have one mathematical equation, okay, Coulombs Law, and we notice it's the force that comes from these electrical particles, okay, and the equation being a constant, okay, times the absolute value of the charge on those two particles, those point charges, divided by the square of the distance, okay? So we look in the back of the book, and then your chapter also gives you the value for that value K. It's in newtons times meters squared divided by Coulombs squared, okay? The charge, the Q, the charges, the SI unit for charge is coulombs, okay? And we notice in our equation, since the constant has newtons and meters involved, okay, the force we're going to get, the electrical force, is going to be registered in newtons. It's going to result in newtons. The R, the radius, we use meters for, okay? So beware of that. Another thing to be aware of, we notice this looks very, very similar to Newton's law of universal gravitation. A constant times the big mass and the small mass over the distance squared between the two gravitational objects, okay? Wow. You know, pretty cool that it results that way. And that, you know, in the early days of discovering of these things, it really excited scientists that, wow, there is an order to these fundamental forces, and it's really been driving them to combine all of the fundamental forces into one equation. It's been very elusive for physicists to this day, but because they see actually this relationship over and over again in these forces in the universe. Okay, so a quick comparison. Know the difference and the similarities between gravity and electrostatic force or electromagnetic force. Okay, we said electricity and magnetism are joined at the hip. Okay, similarities I have written here in white. Okay, both of them are a fundamental force of the universe. Okay, both of them are central force. Okay, they act toward the center of the body. Gravity, the center of the mass. For electrical charge, toward the center of the charge, okay, of the object that has that charge. Because of that, both are a conservative force, okay. Both of them are forces as well as their inherent nature's characteristics of matter itself. Okay, matter has mass. Anything with mass has that force of gravity associated with it. Okay, inherent in all matter at the elementary subatomic level is that charge associated with elementary particles. Okay, so there is a force with that as well. Because of this distance relationship, both electromagnetic forces and gravity forces have no limit on the distance in which they act. They are limitless. Okay, we learned in gravity, it doesn't matter how far you get away from another object, you can never escape its effect of gravity on you. You can get it really, 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 really small, but you can't get it down to zero. And the same holds true with the electromagnetic force. Okay, and then this last one is the equations for force related to those fundamental forces. They're exactly the same format. Okay, they have the constant, they have the two quantities, they have the distance squared in the denominator. Now they do differ though. Okay, in strength. We mentioned the gravity of the four fundamental forces is by far the weakest. The electromagnetic force, the second strongest. Okay. Gravity is only an attractive force, pulls objects to each other, but the electromagnetic force, electrostatic force, as well as the magnetism, as we'll get into later, they can attract or repel. Okay, and of course, for gravity, in the equation for gravity, there's only one kind of mass. It's a positive mass. Okay, even though they have antiparticles, okay, they have protons and antiprotons, they have electrons and anti-electrons, they call positrons. Even though that's the case, the antiparticles have positive mass. So there's only one form of mass. There's only one kind of mass, but there are two types of electrical charge. Okay, so those are kind of the similarities and differences between gravity and the electromagnetic force, okay, of which the electrostatic force is 1/2 of that. So I keep saying electromagnetic because we'll see they are joined at the hip, okay? Electricity, the electrostatic force is 1/2 of it. The magnetic force is the other half. We'll see how they actually are combined a little bit later on. So those are all the notes I had. If you would like I said, you can start reading ahead. Lab 4.1 is a real simple lab. We're going to be doing those friction experiments with the rods and charging rods electrically, and then bringing other charged rods in close proximity to them. We're going to be charging things and transferring that charge to our electroscope, and you're gonna basically be verifying our laws of charges, and that the fact that there are the two charges that like charges repel, unlike opposite charges attract, and that neutral bodies will be attracted to either of those charges. Okay, so that's all I had for now. We'll be talking to you later. Shoot an email or a text message with any questions. Bye for now.